In today's class, we're going to wrap up an idea in Chapter 12 by looking more closely at unit cells. In particular, we want to be aware of three different types: primitive, face-centered, and body-centered cubic unit cells. That'll take just a little bit of time, and then we'll move on to some practice questions that we have in Chapters 4 and 5. We've seen previously that when we're thinking about a crystalline lattice, we have a unit cell that is repeated again and again that fills up all of the space. Here's some of the two-dimensional unit cells that we could have, perhaps being square or hexagonal. By repeating these again and again, it fills up all of the space and gives us the crystalline lattice and the crystalline solid. That was in 2 dimensions. Here's shapes that we could have in 3 dimensions that are being repeated again and again. These are once again used to describe the crystalline solid. We see that shown on the top left for the ionic compound sodium chloride. Now notice within that representation, the illustrators clearly made the cations and anions different sizes. That was something that we've seen earlier in the course back in Chapter 7. Can you explain why the cations and anions here are different in size? Here we have 3 different cubic unit cells. They are called primitive, body-centered, and face-centered. Notice within each of these they have these little dots, which are called lattice points, at different parts of the unit cell. For the primitive, we have 1, 2, 3, 4, 5, 6, 7, 8 on all the corners. With the bodied center, we have those 8 and then 1 in the center. In the face-centered, we have those 8 and then 1, 2, 3, 4, 5, 6 on all of the faces, just like you'd have with a dice. We want to be familiar with each of these. I find it helpful to be able to just make a little sketch. So this would be the primitive. This would be a face-centered. That helps me remember the different shapes. These are going to be useful when we think about how many atoms we have in a unit cell. Let's consider if we have an atom at this point here in the unit cell. It would not be entirely within that single unit cell. It would be overlapping with its neighbors. So we need to consider, if it's on that corner, how many neighbors is it also part of? If it's on that corner, it would be part of 4 different unit cells that are all within the same plane. And it would be also part of 4 that are in the plane below it. So when it's set on that corner, a particular atom would be part of 8 different unit cells. That's what's being described here. And this is how we count the contribution of atoms when they're in neighboring cells. If we have an atom that's on a corner, we've just seen that that particular atom would be divided amongst 8 different unit cells. And that would lead to its fractional contribution. What if it was located in the center of the unit cell itself? In that case, it doesn't have to be shared at all, so it would contribute entirely to the unit cell. And in this case, we see, what if it's located along the face? If it's along the face, it would be shared just between 2 different unit cells. Now, I know this is a new idea for you, so let's practice it. Let's count the sodium cations that we have in this particular unit cell. So in order to do this, we need to see where are they located. If we look at the sodium, that's what's shown on purple, we see that we would have unit cells, sodium atoms, 1 entirely within the unit cell. So in that case, we don't have to worry about any fractional contributions. The 1 in the center is entirely within the unit cell. But let's look within the other ones. We see that we have different ones that are found on these particular edges. I see 1, 2, 3, 4 on the top, 1, 2, 3, 4 in the center, and 1, 2, 3, 4 at the bottom. Each time it's found on the edge, it would be split between a total of 1, 2, 3, 4 different unit cells. So it would have a 1/4 contribution. Since I have a total of 12 of them, each with a 1/4 contribution, that gives me a total of 3 sodium atoms coming from the ones that are on the edges. So within this unit cell, I see a total of 4 sodium cations. Give it a try here for the chloride anions. If we were to see where are they found, we have 1, 2, 3, 4, 5, 6 found on the faces and 8 found on the corners. What would be the fractional contribution for each, and how do we use that to get to the empirical formula? Each of the ones that is along a face is shared just between that unit cell and the immediate neighbor, so it would have a 1/2 contribution. 6 along the faces at 1/2 gets me a total of 3. And the ones along the corners, if it's along a corner, it's each a 1/8 contribution. So that would reach a total of 1 chloride atom for that. We have, therefore, within the unit cell, a total of 4 sodium and 4 chloride. Simplifying that gets us to the empirical formula. We know that the empirical formula for sodium chloride is 1:1, and this is how they're accounted for within the unit cell. Let's practice this a couple more times. It's interesting that the density of the unit cell, that would be the same density as a macroscopic piece of sodium chloride. So we have this question, how many sodium atoms and chloride atoms do we need to reach the density of sodium chloride? It depends on their arrangement, and we know their arrangement once we have the unit cell. I'd like you to give this one a try. This is an ionic compound, nickel arsenide. There's 2 different representations for it here, 2 different views to help you see where the atoms are found. I'd like you to answer, how many nickel atoms are in the unit cell? How many arsenic? And use that to get the empirical formula. We have a side view and a top view. If we're counting up the nickel, we see that we have atoms on the corners, a total of 1, 2, 3, 4, 5, 6, 7, 8 along the corners, each of those with a 1/8 contribution. Gives me a value of 1. And I have 1, 2, 3, 4 along the edges, each of those with a contribution of 1/4. So I have a total of 2 nickel atoms within the unit cell. If I'm looking for arsenic, both of those are entirely within the unit cell. It might not be clear from the picture here on the left with the side view, but it's clear from the top. So both of those are entirely within the unit cell. That gives me 2. Total of 2 nickel atoms and 2 arsenic. So the empirical formula is 1:1. Here's one more for you to try. What's the empirical formula when we have titanium and oxygen shown in the unit cell here? 2 different representations for you. And as a hint, 2 of the oxygen atoms are entirely within the unit cell. For the titanium, we have those being found at the corners, 1, 2, 3, 4, 5, 6, 7, 8, each with a 1/8 contribution, and there's 1 in the center, so there's a total of 2 titanium atoms. We could also see that with the image here on the right, where we have the 8 being shown in blue, and then 1 in the center, to give us a total of 2. For the oxygen, how do we account for those? We have 4 of them found along the faces, 1, 2, 3, 4, or perhaps more easily seen at the one on the right, 1, 2, 3, 4, and then 2 that are found entirely within. 4 along the faces, each with a 1/2, 2 entirely within gets me a total of 4. So for titanium dioxide, the formula is TiO2. If I were to assign oxidation numbers for this, each of the oxygens is -2, so the titanium must be +4. That's what we want to know when it comes to interpreting unit cells and using them to come up with an empirical formula. For the remainder of the class, let's work on some practice questions that we find from chapters 4 and 5. Within the provided questions, there's 2 versions for each one. The first one is something we might find on the exam. The second one might be related and a little bit more advanced, or in some ways looking at the topic in a slightly different way. If we look at this case right here, which of the following is a weak electrolyte when added to water? To answer this, we need to be able to remember what makes something a strong, weak, or non-electrolyte and classify it. The related question, which of the following has the highest concentration of chloride ions, it begins with that assignment. We need to first think about these as strong, weak, or non-electrolytes, and then connect it to the concentration. So that makes it a slightly more advanced question. Give it a try as you go through, and we'll be happy to help you.